So let's say I have a binary tree. Let's say I have a tree that has a root, and then every node in this tree has at most two children, a left child and a right child. So this root can have two children. Then maybe this one has one other child, and maybe this one has two children of its own, and so on. Now we can easily implement this using pointers. I can have an object or a class or a struct, which basically models one node of this tree. And then every node will contain a pointer to the left child and to the right child. And maybe you would also like to have a pointer to the parent, right? But if these trees are of a very specific form, and this is what we call a tree, then there is a better way. Okay, so what is a complete binary tree? Well, it's basically a tree in which all of the non-leaves have exactly two children. So this is not a complete binary tree, but if I add this one, then it would be a complete binary tree. Now, in general, this means that when I'm talking about a complete binary tree, if I look at the different levels of this tree, let's say I call this level 0, I call these two nodes level 1, and I call these ones level 2. So basically the level of a node is just the distance between that node and the root, right? So I say my tree is complete if at every level I have 2 to the power of number of that level different nodes. So I have 2 to the power of 0 nodes at level 0, which just means that I have one root. And then I have 2 nodes at level 1. I have 4 nodes at level 2. And generally at level I would have 2 to the power of I. Now, this is what we call a complete binary tree. But sometimes we like to also have binary trees that are not really complete. Let's call them almost complete. And this means that in my last level, I might not have all of the nodes, right? So maybe I have something like this, right? I don't have all the possible nodes in the last level, so the last level is not complete. But the nodes that I have to be left justified. It should be all the nodes on the left. So basically, I cannot have, for example, I don't know, this node without also having this node first, right? So if that's the case, I say it's almost complete. Now, if I have a binary tree that is almost complete, I actually have a better way of representing it. Instead of just using pointers, I can do something better. So here's the thing. I can suppose that I want to save a number at each one of the nodes of this tree. I can just save it as an array. I can just assign one array index to every node of this tree. And this is how I'm going to do it. I'm going to say my root gets index 1. And then the children of the root get indices 2 and 3. And then this one gets index 4, this one gets index 5, 6, 7, and so on. 8, 9, 10, 11, and 12. Now, what's really nice here is that if I have a node that has got index I, so let's say I have this node, and let's say it has 2 children, and of course, it also has a parent, right? So let's say this node has index I. The index of the left child will always be 2i, and the index of the right child will always be 2i plus 1, right? And of course, the index of the parent will always be I over 2. And this is actually really nice, because it means that I can save this tree data structure in an array. So from the point of view of my code, I just have an array. But in my mind, I'm thinking of it as a tree. And this allows me to avoid saving all those pointers and thinking about pointers and things like that. So basically, whenever I want to go to the parent, I just divide the index of the current node by 2. Whenever I want to go to the left child, I multiply by 2. Whenever I want to go to the right child, I multiply by 2 and add 1. It's a very simple idea. Okay. So from this, let's actually go to heaps. So what is a heap? And actually, I'm going to start with a max heap, but you can define a min heap very similarly. It's basically an almost complete tree such that we have saved one number in each of the nodes, okay? So let's say I have an almost complete tree, something like this. And let's say that I save a number at each one of them. Now, the rule that I want to be satisfied is that I want every node to have a number bigger than or equal to the numbers in its children. So let's say the numbers that I have are something like this. So I have 10 here, maybe 5 here, 8, 1, and let's say I cannot have 6, let's say 4. Okay. So I say it's a max heap if it's an almost complete tree, and the number that I've saved at any node is bigger than the numbers in its children, or it can also be equal. I allow equality. Okay. So this is the very first data structure that we're going to see in this course. Now, of course, if I have a max heap, I would like to do a bunch of things with it. So I have to tell you what operations I like to do. I like to be able to add new numbers. Okay. So that's the first operation. So let's say the operations that I want to support. I want to support, say, insert. And insert x basically takes some parameter x and adds x as a new number to my heap. I want to be able to delete from my heap, but this is going to be kind of restricted. I can only delete the maximum element, okay? So I'm going to have an operation called delete max. Or actually, I'm too lazy to write delete every time, so I'm just going to call it pop max. So pop max, it doesn't take any parameters, it just removes the maximum elements, okay? And yeah, that's it for now. We can add other operations later on. But for now, let's say I just want to be able to do these two things. And well, oh, really importantly, I want to also have get max, right? Which just tells me what is the maximum element. But that's easy because my maximum element is always at my root. So if I save this as an array, I know that my root is always at index 1. So I'm using blue for indices and black for the actual values that are saved there. So this is index 1, this is index 2, 3, 4, and 5. So if someone asks me what is the maximum number saved in this heap, I know that by the heap property, my maximum number is always in my root. And I know that my root is always at index 1. So get max is super easy. I just return the element at index 1. So if I'm saving this heap in some array called h, basically my pseudocode would be something like this. Get max is literally one line, return h1. Right, that's always my maximum. Of course, assuming that my heap is not empty. If it's empty, then, well, I'm returning some garbage. Right. Okay. Now, let's do insert. Suppose that I have this heap, and let me see if I can actually copy it, because that's the whole point of doing this. Is this for selection? Hopefully. No. No, it doesn't work. I have to use this. Yes, okay. So this is from the last session. Let me delete this one. Let's do insertion. So I want to insert something into this heap. And let's say that this was my original heap. I don't know why it didn't preserve the colors. I literally copied it from the previous slide, but then it copied it in the same color. Okay, whatever. There's nothing I can do now. So, and this get max just gives h1. Okay, So I want to insert something here. Let's say I want to insert a really large number. Let's say I want to insert 12. Right. Now, the problem is that I know that eventually, since 12 is my largest number, it will end up at the root. But where can I add 12? You see, the problem I have is with the structure of my tree. The structure of my tree is fixed based on the number of elements. So if I tell you that I have a heap with n elements, those n elements have to be at indices 1 to n, because that's how I want to save it in an array. And if they're in indices 1 to n, that means I have an almost complete tree. So the structure of the tree is fixed. There is only one almost complete tree with n nodes. So if I want to add a new element, what's going to happen with the structure of my tree is that this node is going to get a left child. Right? So, but I know that the new element that I want to add shouldn't be there, because maybe, again, this is the example that I'm doing. I'm trying to insert 12. So let's say I just insert 12 here. I insert 12 at index 6. Now I have a problem. The problem is not with the structure of the tree. The tree has the correct structure. The problem is with the heap property. And the heap property was that every node should have a value that is bigger than its children or equal to its children. And this heap property is violated here, 12 as a child of 8. Okay. So how can I fix this? I can just swap 12 and 8. Right? So I insert 12 here, and then I delete it and like basically swap it with 8. So put 8 here, put 12 up here. But this doesn't solve my problem. It just pushes my problem up, right? I don't have a problem between 8 and 12 anymore. It's fine that 12 is the parent of 8. But now I have a problem with 12 and 10. But I can solve it in the exact same way. Just swap 12 and 10. Right? So I just swap the 12 and 10. So 12 comes here, 10 goes here. And now finally I have a heap again, and I'm happy. Right? Let's try inserting something else. Let's try inserting now, let's say 11. So I insert 11. Well, again, the structure of the tree tells me that I have to insert 11 here. I have to insert it at index 7. So I add 11 here. Now I have a problem. 11 is larger than its parent. So I just swap 11 and its parent. So 11 comes up here, 10 goes down here. Now I no longer have a problem because 11 is actually now smaller than its parent. So it's not like every time I have to swap it all the way up. I can just do it part of the way, as much as necessary. Right? So this operation of taking some element and comparing it with its parent, and if necessary, swapping it and continuing to do this, this is called bubbling up. Okay. I don't know why it's called that. It's just that the first guy called it that, and everyone calls it that. So basically, my insertion is that I always insert at the correct index to make sure that I have the correct structure for my tree. And then I take the new element that I have inserted and I bubble it up. So let's do another insertion. Let's say now I want to insert 7. Okay. So where should I insert it? Since I should have indices from 1 to 7, and now this is the 8th element, I have to insert it at index 8. But index 8 is going to be the left child of index 4. So I have to insert it here. Right? So this is index 8. But in index 8, I have to insert the value 7. Now I take 7 and I compare it with its parent. I see that the parent is 1, so 7 should go up. So I have to put 7 up here and 1 down here. Now, again, I take 7, I compare it with its parent. I see that it's still larger than its parent. So I put 7 up and 5 down. Now I compare 7 with its parent and I see that I no longer have a problem. So that's great. This is a heap. Okay. So this is how I insert something. Now let's talk about the runtime. Let's say I have n elements. If I have n elements, what is the height of my tree? How many levels do I have in my tree? Log n, yes. And that's pretty easy to prove. Actually, I'm just going to say O log n because I never want to talk about the -1 or +1 in logs. So we have a logarithmic height. Because basically every level has twice as many nodes as the previous level, except for the last level. But the last level, that's fine. We can just ignore it because it has at most half of all the nodes. So when we're doing asymptotic analysis, we can just count the nodes outside of the last level. And that would already tell us that the height is logarithmic. Okay. Now, so that means that every time that I'm bubbling up, I'm taking some item and I'm moving it up at most log n times, right? So based on that, I know that every time that I'm inserting something into the heap, the time is going to be O log n. So the time for insertion is going to be O log n, where n is the number of elements. Okay. Nice. So our insertion, it's not bad. It's kind of fast. Not as fast as I would like it to be, but it's okay. We will talk about other data structures later that would actually even faster insertion. But let me just copy this again and go to the next slide. How come this time it preserved the colors? I don't know how this app works. Okay. So now let's say that I want to delete the maximum elements. Okay. So I want to do pop max. Right. So I want to remove 12. If I want to remove 12, I have a problem. The problem is that if I just remove 12, like if I just erase it like this, I now have two different heaps. And now I have to think about how to merge them and everything gets messy. This is too hard. But again, I just think about the structure of my tree. I say that right now I have 8 elements in my tree. After I remove the maximum element, I should have 7 elements. So if you ignore all the numbers in the tree, the structure of the tree should basically be a tree that doesn't have this node, right? So again, I prioritize the structure and I say I have to delete this node. But the problem is that if I delete this node, I'm deleting 1. I want to delete 12. So I first just swap 12 and 1, and then I delete this node. So I first swap 12 with 1. I put 1 up here. I put 12 down here. And then I remove this node. Now, again, my heap has the correct structure, but I'm violating the heap property. I have this problem that I have this really small number 1 at the top of my tree, at the root, and it's not bigger than its children. So what should I do? I have to take 1 and move it down. Okay, so this is what we call bubbling down. And it's very simple. I take 1, I say, well, you cannot be larger than your children, 7 and 11. So we have to swap it. We have to swap it either with 7 or with 11. But which one should I take? I should take 11, yes, because I want the largest possible value to be at the top, right? So if I swap 1 and 7, I will still have a problem that 7 is smaller than 11. But if I swap 1 and 11, I wouldn't have any problems. So let's just swap 1 and 11. So I always swap with the largest child. I put 11 here, and I put 1 here. Now you see here on this side, I'm happy because 11 is bigger than 7. On this side, I'm also happy because 11 is bigger than 1. But the problem is with 1 and its new children, right? So 1 is now smaller than 8 and 10. So I just do it again. I take the maximum of the two children and I swap it with 1. So the maximum of the two children is 10. I swap it with 1. 10 comes up here. And 1 goes down here. And now finally, again, I have a heap. Right? So this is very similar to the previous step. It's just that instead of taking an element and moving it up, I'm taking some element and moving it down the heap. And every time as I'm moving it down, I have two choices. I can swap with the left child or the right child. But I want the maximum value to come up, so I just look at the maximum of the left and right child. Okay. This is great. Now, how much time would this one take? This is, yeah, exactly. It's basically the same because, look, the height of my tree is log n. If I take a node and I ask you how many times can I go up, log n times. How many times can I go down? At most log n times. So it's the same. So again, my time is just in O of log n. So I can remove the maximum element in time log n. I can add a new element in time log n. So let me just put these things here. So log n for insertion, log n for taking out the maximum element. How much time did I need for just getting the maximum element? Yes, that's constant because I'm just literally returning the element at position. Okay. Great. So we can use this to actually sort an array of numbers, right? So if I have an array, I can just create a heap and I can insert the elements one by one into the heap. So I do n insertions. And after I do that, I can take the maximum out n times. Right? That gives me actually a reverse sorted array. So if you want to sort from minimum to maximum, you can then reverse everything. Right? But generally speaking, this is what we call heap sort. So heap sort is a very simple algorithm. It just says, if you have as your input some array A, let's say an array A of n items. Okay, and as output, you want to sort A. Okay, so a sorted permutation of A. This is just what we've seen before. All I do is this. I create an empty heap. So this is my pseudocode. I'm going to call it HS for heap sort on A. And let's say I also have N. I just create an empty heap, H. And then I keep adding all of the elements into this heap. Okay. So for every number X that is in the array A, I just say H.insert X. Okay. Now I have all of my numbers in a heap instead of just an array. Now I can just take the maximum item out every time and just print it. So I say, as long as my heap is not empty, while the heap is not empty, do this. Print the maximum element, so h.getMax. And then after you print it, remove it. So h.popmax. Right. This just prints all of my numbers from maximum to minimum. And if I want it from minimum to maximum, I can just save them somewhere else, reverse them, and print it. Or alternatively, I can just change the definition of my heap. So I told you that this is a max heap. And I said that the reason we call this a max heap is because every node is greater than or equal to its children, right? So it means that the maximum element would always be at the root. Now I can define the opposite thing. I can call it a min heap. And I just say my rule is that every node should be less than or equal to its children. And then my minimum element would be at my root. And all the same algorithms would work, except that instead of pop max and get max, I will just have pop min and get min. And again, I want you to really realize that nothing has to change in the other algorithms. So if I insert something in a min heap, again, I insert it in the exact same way and I bubble it up. It's just that the rule for bubbling up is different because now every node has to be smaller than its children. And if I want to delete something, I first swap it with the root, swap the last elements with the root. I delete the last element, and then I take the root and bubble it down. So everything is basically the same. Okay. Great. So let's code this. Again, you cannot see my entire screen. Okay, I'm going to just code the heap sort in general. And by the way, a lot of these algorithms are already implemented in the standard C and C++ libraries, but I'm going to implement them again anyway, because I just want to show you how to do this. So let's say I use a vector for my heap. And let's say I have some n, and I create a vector of integers called h, which is my heap. And originally, I just say, let's put a 0 at position 0 because I want to use indices starting from 1. So I'm just putting a 0 there, right? And I say just read a bunch of numbers. So for I from 1 to n, read some number and add it to the heap. So I'm going to just call it insert hx. So insert x into h. And then I'm literally just coding this. After inserting everything into h, I say as long as h is not empty, take the maximum and remove the maximum. So I say while h.size is greater than 1, because now I have this 0, the pesky 0 at position 0. So I say as long as the size is at least, just write h, or I'm just calling it get max of h. And then do pop max h. Okay, so that's my sorting algorithm, assuming that I have get max, pop max, and insert implemented. So let's implement these. So let's say I want to insert into, actually, let me do something cheeky here. I want to say, whenever I say heap, I mean a vector of integers. Okay, so I have a heap h, and I also have some number x, and I want to insert x into h. Right? So this was actually very obvious. We just said that we always add x at the last position. So if the last index was 7, I would add x at index 8, right? This was here. So now if in this heap I want to add something else, I would add it at index 9 and so on. So I just say h.pushback x. So this adds x to the last place in h. And then I have to do this bubble up thing, right? I have to take x and I have to compare it with its parent and keep doing that. Okay, so what is the index that x is put into? It's basically h.size minus 1, right? So I have something at index I, which was added recently, and I want to take it and compare it with its parent. So I just do a while, and I say as long as, well, for how long would I move this thing up? I would move it up as long as it's not already the root, and as long as this value is bigger than the value of the parent, right? So I would say while I is not 1, which means while I'm not at the root, and the value here, hi, or actually x, is greater than the value at the parent, hi over 2. What do? I just swap hi and hi over 2. So I'm moving it up, but I should also update my index because now I have to point to the parent for this. So this is bubble up. Again, 4 lines of code. Very easy. So this was my insertion. Now let's do, well, actually, let's do get max first. That's easy. So if I want to get the maximum element in a heap H, I would just return H1. And actually, this doesn't change the heap, so I can also put a const there. Okay. And then I have pop max, which removes the maximum elements. So I would have void pop max, and I have a heap H. Okay. Let's first find the index of this last element. So it's at index h.size -1, basically. And all of this -1 business is because I want to name everything from index 1, so on. So let's say my element is at index n. So what do? I just swap it with the root, right? So I would first swap whatever is in the last place and whatever is in the first place. Now I remove the last place, so h.popback. I'm just removing the last item in my vector. And now finally I have to bubble down, right? So I'm in this situation. I have, let's say, again, let me do another example here. Let's say I want to remove this 1. I first swap it with the 11. So I've already coded this. 1 comes here, 11 goes down here. That's what this line is doing. And then I'm removing the very last item. So I'm removing this one. And now my problem is with my root. My root might not be bigger than its children. Okay. So again, I start by taking some index I item that has a problem. And I have to constantly move this down now. Okay. Now let's say this n, which was my maximum size, let me also decrease that so that n actually gives me the number of items that I have. I can use it later. So I'm going to again have a while, but when would I push the item at index I down? I would push it down if it's either its left child or its right child. But I have to also check if these left and right childs actually exist or not, right? So the condition that I have to actually write in this while is to say if a left child exists and I am smaller than the left child, or if a right child exists and I'm smaller than the right child. We can write this in a simpler way later, but let's just write it like this. So how would I say that a left child exists? How can I check if the item at index I has a left child? Well, if it does have a left child, the left child should be at index 2 times I. But my indices are from 1 to n. So if 2 times I is less than or equal to n, I do have a left child. Okay. So that's good. The other case is I want to check that I have a right child, and the right child would be at index 2 times I plus 1. So again, I check if 2 times I plus 1 is less than or equal to n, I do have a right child. But I'm not going to write it in the while condition here. Let me just write the inside and then we'll talk about that. So here's the thing. Whenever I have an element that I want to bubble down, I have at most 3 elements in play. I have this element itself, its left child, and its right child. And I want to know which one among these 3 is the maximum. I always want the maximum to be at the top, right? So let's just do that. Let's show that maximum with I, and let's see if it changes. So I say if there is a left child, if I times 2 is less than or equal to n, if I have a left child. And additionally, if that left child is bigger, so h of I times 2 is bigger than h of I. Okay, then I say my maximum is now my left child, sorry, I times 2. Fine. Now, I want to again check. I say if a right child exists, if I times 2 plus 1 is less than or equal to n. And additionally, the value in that right child is bigger than the value at whatever maximum value I've had until this point, right? Then the maximum actually becomes the right child, right? Now, what should I do? I have to say, there are 3 cases. If the maximum element is already element I, I'm happy, right? Because element I was bigger than both of its children, if they exist, right? So if at this point the maximum is I, I'm happy and I just break. I say, you don't need to do anything. Otherwise, I have to swap the element at M with the element at I. So I just swap HM and HI. And then I have to say I equals M for the next iteration of the while loop because I want to keep doing this. And then my while condition is just going to be while 1. So do this until you break. Right? Okay. Now, normally I don't like to constantly write I times 2 plus 1, and like I over 2. These things are a bit confusing, so I would just define macros or functions for them. So I can just say I define P for parent, and P of I is just I over 2. I define L for left, and left of I is just I times 2. And then I define R for right, and right of I is just I times 2 plus 1, right? So normally, I would write this in a much nicer way. So let's actually go over this and fix it. So when I'm inserting something, I'm inserting X, and I points to where this newly inserted element was. And I say, as long as I'm not at the root, and as long as the value is bigger than the value at my parent, I'm going to swap the value with the value at my parent. And then I'm going to go to my parent, right? So I would prefer to write it like this. And here again, when I'm doing the pop max, I swapped the first element and the last element. I removed the last element. And then I'm taking the first element, the root, and moving it down. So every time, this is at index I say if the left child exists, of I is less than or equal to n, and the value at the left child is bigger than the value at I itself, then my maximum index is the index of the left child. And also, if a right child exists and the value at the right child is bigger than the maximum value, then the maximum index becomes the right child. If the maximum index is I, it means that I've bubbled down as much as needed. I don't need to bubble it down anymore. Otherwise, I swap. And so, okay. Let's see if this works. I hope it does. Let's say I have 5 elements, 1, 2, 3, 4, 5. Yes. Okay. So this is how we create a simple heap and add elements into it and remove elements from it. And of course, I did this with a vector. You could just do it with an array. But if you do it with an array, you have to also keep track of your n, like what is the size of my heap. Okay. Let's go back here and let's actually ask something else. So I told you that I'm thinking of these heaps as a special type of tree. I'm thinking them as almost complete binary trees that have this additional property that every node is bigger than or equal to its children. Okay. But I'm actually saving them as an array or a vector in my code. So it's obvious that some vectors or some arrays are heaps and some of them are not. So the question is, if I just give you an array and I ask you to make it into a heap, how much time would you need to do that? So this is the operation that I'm going to call make heap. So make heap just takes an array A of size n and asks you to turn this into a heap. Okay. Now, a very simple thing that you can do is to just start with an empty heap and keep adding the items in the array. That's what I did in my heap sort, right? Every insertion is going to take log n time, so you're going to spend n log n overall. So I can definitely do this in O of n log n. But the question is, can I do any better? So let's say I just give you an array. And of course, you can always visualize it as a tree, right? So let's say I give you this array A, and it has some numbers in it, 5, 2, 6, 1, 0, 7, 9, another 2, let's say, okay? I can always turn this into a tree. I can always say, okay, so this is index 1, index 2, 3, 4, 5, 6, 7, and 8. So I have this kind of situation. I have 5 at index 1. Then at index 2, I have 2. At index 3, I have 6. At index 4, I have 1. At index 5, I have 0. At index 6, I have 7. And at index 7, I have 9. And finally, at index 8, I have 2. Okay. So if I give you any kind of array, you can, of course, visualize it as a tree. But then that tree would not be a heap. So the question was, I want to turn this into a heap. How much time do I need to do that? Now, our first solution was just start with an empty heap, keep inserting elements. And inserting each element takes log n. I'm inserting n elements. It's going to be n log n. But what if I just want to do it on this array itself? You see, one thing I can do is to start from the top and just bubble up all of my elements, right? So I can start here. I can say I do bubble up on 5, but 5 is already at the top, so it doesn't move. Then I do bubble up on 2, but 2 is less than its parent, so it doesn't move. Then I do bubble up on 6. 6 is actually bigger than its parent, so it gets swapped. So 5 comes here, 6 goes here. Then I do bubble up. So 1 is smaller than its parent, nothing happens. I do bubble up on 0. 0 is smaller than its parent, nothing happens. I do bubble up on 7, and I see that 7 is bigger than its parent, so I swap. So 7 goes here, 5 goes here. But I have to continue the bubble up. So now I compare 7 and 6. I see that I have to swap them too. So 7 goes here and 6 goes here. Okay. Now I have to do it with 9, right? So I do bubble up on 9. I see that I have to swap 9, and 6. So 9 comes here, 6 goes here. I continue the bubble up, 9 and 7. So 9 goes here, 7 comes here. And then finally, I have to do bubble up on this 2, and 2 is bigger than 1. So I swap them. And now I don't have to move it up anymore. So this algorithm was actually quite easy. You just start at the top of your tree and you call bubble up on everything, right? Now, if I want to just write a pseudocode of this, it would be something like this. I have make heap, and I have some array A and N, and I just say for every index for I from 1 to N, just in the array A, call bubble up on index I. Because I told you that I want to do this from the top of my tree down, but that's basically like in the same order of indices, right? 1, 2, 3, 4, 5, 6, 7. Okay. Now, 2 questions. First question, why is this correct? And second question, what is its runtime? Now, in this course in general, when you write homeworks or final exam papers, you have to always prove the correctness of your algorithm, and you have to also always argue what the runtime is. So first of all, why is this correct? Why would it give me a heap at the end if I just do bubble up on everything? Well, here's what I can say. I can say that after I do bubble up on I can always prove that at this point, the heap that is consisting of A1, A2 to AI is actually a valid heap. I shouldn't have called it the heap. Well, the array is a valid heap, right? Because if you think about it, this is basically the same as the insertion, right? So when I'm doing bubble up on index 1, imagine that the rest of this heap is not there. So I'm just inserting something into an empty heap, and then I'm bubbling up. Now, when I do bubble up on index 2, again, imagine that indices from 3 to 8 are not there. So I'm just inserting this new thing and bubbling it up. And the same thing happens over and over again. So this algorithm is no different than the insertion algorithm. It's going to give me the exact same result. And of course, I know that if I insert n things into a heap, I have a heap at the end. So this algorithm is definitely going to give me a heap at the end. But now the problem is that it's going to give me the same bad runtime, right? Because this is basically inserting n times. And I said that inserting n times takes n log n. But if we want to be more specific, let's just see how many times each of my elements can get bubbled up, right? So I have a level. So I have level 0 here, level 1, level 2, and level 3. And remember that my level was always the distance to the root. And then I have some number of elements. And as before, we've seen that in level 0, I'm going to have 1 element. In level 1, I'm going to have 2, then 4, and so on. Generally, at level I, I'm going to have 2 to the power of I, right? So let me write it like this. At level I, I'm going to have 2 to the power of I elements. And it goes down to, let's say, let's call this k, level k minus 1, I'm going to have 2 to the power of k minus 1. And then at my last level, at level k, I have at most 2 to the power of k, because maybe the last level is not 4, right? But now I want how many times can an item in level 0 be moved up? If I have an item at level 0, it can never be moved up. Okay, so I want the number of moves, and it's just 0 here. An item at level 1 can be moved up at most once. So the number of moves is 1 here. An item at level 2 can be moved up in the worst case twice. It can go all the way to the root, so it's 2. And generally, an item I can be moved up I times. So what is the total number of moves? What is my total runtime? It's basically something like this. It's the sum of I times 2 to the power of I, right? Because at level I have 2 to the power of I items, and each of them can move up by I steps. And this is for I from 0 to basically log n, but I'm going to call it k, right? Now, the problem is that this sum is actually theta n log n. And you can prove that very easily. So this is in theta of n log n. Okay. Where k is basically log n. Okay, so remember k is the height of the tree, and it's in theta of log n. Okay. So I'm not happy about this. But what is the problem? The problem is that as I'm going down the tree, I'm going to have more and more nodes, right? But my nodes are also getting more expensive. Because if I look at the root, if I look at a node that is close to the root, I'm going to move it up very few times, right? But as I'm going down the tree, the number of my nodes is increasing exponentially in every level, but my cost is also going up. So I would like it to be the opposite of this. I would like to have a situation where I spend less time on the nodes that are closer to the bottom, and I spend more time on the nodes that are close to the top, because I have very few nodes close to the top and a ton of nodes close to the bottom, right? So here's the second idea. Let's again take the same array as before. Let me see how I can copy this. Do you think the color will change? No, it preserved the color. It was a one-time bug. Okay. So let's do this again. Let's create our tree. So I have 5, 2, 6, 1, 0. So I have 1 here, 0 here, 7 here, 9 here, and a 2 here. Okay. So previously, I started at the top and I said I do bubble up on everything. Let's start at the bottom now, and let's do bubble down on everything, right? So why do I want to bubble down? Because I said I want to pay less for the nodes that are close to the bottom. And bubble down is cheaper if I'm closer to the bottom. So I prefer to do bubble down. So let's do that. So this is my new algorithm for make heap. I'm going to just write the pseudocode here. Make heap an. It's just going to say start from the end. So start for I from n down to 1. And every time do bubble down. So a dot bubble down on index I. Okay. Let's first do it on this example to just see even, does it really work? Does it not work? What's going to happen? So I'm going to start with this 2 and bubble down, but there's nothing down, so it just remains as it is. And then the same thing happens with 9, 7, and 0. So I want to bubble down, but they don't have any children, so it just remains as it is. Now I do bubble down on 1. I see that it's smaller than its child 2, so I swap 1 and 2. 2 comes up here, 1 goes down here. Okay. Now I have to do bubble down on this 6 now. So 6 is smaller than its children. I just take the maximum of the children and swap it with 6. So 9 comes up here, 6 goes down here. There's nowhere else to go. There's no more bubbling down here. I do bubble down on this too, but it's already fine. It's already bigger. The same for this 9. It's already bigger than its children. And then I do bubble down on this 5, right? So 5, I see that 9 is bigger, so I just swap them. 9 comes up, 5 goes here. I have to continue bubbling down, so I see that 5 is smaller than its 2 children. I take the maximum, which is 7, and I swap it with 5. And this is finally a heap. Okay, so first, same heap as before. 9, 2, 7, 5, 6, blah, blah. Yeah, it's the same heap as before. Bad example. Generally, it wouldn't be the same. Okay. So on the same set of numbers, you can have many different heaps. So I don't know how I just randomly wrote something that gave us the same. But now, again, we have the same problem as before, the same 2 problems, actually. You have to prove that this is a correct algorithm, and you have to figure out what the runtime is. So first of all, why is it a correct algorithm? Why does this give me a heap at the end? So you see, previously, my argument was that I was saying after every iteration of this loop, there is some part of my tree that is an actual heap. I want to do something similar for this loop. I want to say that after I do this bubble down, there is some part of the tree that is definitely a heap. Okay. What is that part? It's basically I and everything below it, I and all of its descendants. So after this happens, I and all of its descendants this whole thing form a valid heap. Now, why is that? Let's look at this. So when I'm doing it on a leaf, it's obvious, right? Because the descendants are only this node, and one node is always a valid heap, right? So this one is fine. So this one is also a valid heap. This one is also a valid heap. This one is also a valid heap. This is also a valid heap. Now, when I want to do bubble down on this index, forget about the numbers, just focus on the structure. When I'm doing bubble down on this one, I already know that the left side and the right side are valid heaps, right? So I'm in a situation, if I just ignore everything above this 7, if I just look at 7 and its children, so I look at 7, 5, and 6, forget about all of the rest of the tree. Okay, that tree basically has the heap property satisfied everywhere except for its root, which is the current node, right? And this is the same situation that we had here when we were doing pop max. When we were removing the maximum element, we would swap the last element with the root, remove the last element, and then we had a tree that had the heap property everywhere except for the root. And then we saw that when we do bubble down, that gives us a valid heap. So the exact same thing is happening here. If I just say, I want to forget about all of this, I have a valid heap on the left, I have a valid heap on the right. I only have this root, which might not satisfy the heap property, and I'm doing bubble down on the root. So eventually, afterwards, I will have a valid heap in this whole place. Okay? So I do this, and then all of this would be a valid heap. Then when I do it on 2, all of this would be a valid heap. And finally, I can say the same thing about my root. I can say the left child and all of its descendants are already a valid heap. The right child and all of its descendants are already a valid heap. So when I do bubble down, everything would be a valid heap. Okay. So that's the proof of correctness. And by the way, I say the proofs in words, but in the homeworks and the final exam, you have to actually write them down, right? So you'll get some experience with this with the homeworks. Our TAs are very picky about how you write. Okay, so now we know correctness, but how much time am I spending? So let's create the same thing as here. So level, the number of nodes, and the number of moves. So I have levels, which is 0, 1, 2, and let's say I have a level I and it goes n. And then I have the number of nodes. At level 0, I have 1 node. At level 1, I have 2 nodes. Then I have 4 nodes. Generally, at level I have 2 to the power of I nodes. In the last level, I might not have all of my nodes, right? And then what is the number of moves? How many times can something go down? Oh, actually, I was supposed to use k here, not n. N was supposed to be the number of elements that we have. K is the log, right? Okay, what is the number of moves? If I start here, I can move down k times, right? So it's k. If I start here, I can move down k minus 1 times. If I start here, I can move down k minus 2 times in the worst case. And generally, if I'm at index I can move down k minus I times. And of course, if I'm already a leaf, or if I'm at the last level, I cannot move down at all, right? So now I have a situation where as I go down the tree, I have more and more nodes, but these are nodes that cannot move too much, right? So as I'm going down, the number of moves that every node can make is also decreasing. So hopefully this is better. What is the total number of moves? If I just want the total number of moves, it's just the sum. And again, at level I have 2 to the power of I nodes, right? But each of them can go down by k minus I steps now. So it's 2 to the power of I times k minus I. And this is for I from 0 to k. Okay. Now, intuitively, this should be better than the previous sum that we had, because in this previous sum, I had a lot of nodes close to the bottom that were moving a lot, right? But here, I have a lot of nodes close to the bottom, but they're moving only a little, right? So this sum is definitely smaller than the previous sum. But what is the value of this sum? I don't remember. So it should be, I had a note about this somewhere. Where did I put it? Well, let me just ask Wolfram Alpha. Or actually, whatever, I can guess it. Yeah. The value of this sum is going to be 2 to the power of k minus 2, k plus 1. Minus k minus 2. Yeah, probably. Let me ask Wolfram Alpha, and then I'll prove it to you afterwards. Wolfram Alpha. What is the sum of I from 0 to k of k minus I times 2 to the power of I? Minus k plus 2 to the power of k plus 1 minus. Oh, I'm really proud of myself. Okay. So let's prove this. Okay, I want to prove that it's this. And now, again, remember that k is log n. So if we prove this, 2 to the power of k plus 1 is basically 2 times n, right? So this means that this whole thing is going to be in O of n. So we got rid of the log factor. We took a whole array, it could be any array, and we're now turning it into a heap in linear time. Okay, assuming that this sum is correct, which is correct because Wolfram Alpha says so. I'm really trusting in Wolfram Alpha. So let me copy this and let's actually prove this by induction. Okay, so I have this. I don't know why it didn't copy the K correctly. So let's prove this by induction. So here's a proof by induction on K. Okay. For K equal to 0 or 1 or 2, you can just check it. It's correct, right? So if K is 0, this is 2 to the power of 1, which is just 2, minus 2, which is 0. And then the sum is also from 0 to 0. And then there's a 0 here, so it's 0. Okay. Yeah, you can check it for small values. It's correct. So let's say that this holds for K, and let's show that it holds for K plus 1. Okay. So this is my induction step. Here's what I'm going to do. I'm going to take the sum of I from 0 to K plus 1 instead of K. And then I have 2 to the power of I, but here I have to put K plus 1 instead of K as well. So 2 to the power of I times K plus 1 minus I. Okay. Now, what is this? Well, first of all, what happens when I is exactly K plus 1? I get K plus 1 minus K plus 1, so I get a 0 here. So this sum is the same as the same sum, but going only up to K. So I from 0 to K, 2 to the power of I times K plus 1 minus I. Okay. Now, I want to make this thing look like this one. My problem is that I have an extra plus 1 in here. So let's just take that extra plus 1 out. So I will have the sum of I from 0 to K of 2 to the power of I times K minus I plus the sum of I from 0 to K, 2 to the power of I times 1, which is just 2 to the power of I. Okay. Now this one, by induction hypothesis, is 2 to the power of K plus 1 minus K minus 2. Okay, so this whole thing is 2 to the power of K plus 1 minus K minus 2. Did I write it correctly? Yes. And what is this one? This is summing up all the powers of 2 from 2 to the power of 0 to 2 to the power of K. So if you look at this number in binary, it's a number that is just a bunch of 1s in binary. Right? So if I just add 1 to it, I will get 2 to the power of K plus 1. So this number is actually 2 to the power of K plus 1 minus 1. Right? So this is my sum. And yeah, so pretty easy. 2 to the power of K plus 1, 2 to the power of K plus 1. I add them together, that would be 2 to the power of K plus 2. Minus K minus 1, that's minus K plus 1. And the minus 2 stands. Right? And this is exactly what I wanted to prove. Right? So if you just take this and put K plus 1 in place of K, you get 2 to the power of K plus 2 minus K plus 1 minus 2. And that's exactly what we got. So, and again, remember that K was the log of N. So 2 to the power of K is N, 2 to the power of K plus 1 is 2N. So this whole thing is in O of N. Okay. So what did we show? We showed that if I already know N numbers and I want to just create a heap of N numbers, it's actually not optimal to just start with an empty heap and insert my numbers one by one. It's much better to do this, right? So I can make a heap of N numbers in linear time. So I can kind of improve my heap sort by just replacing this part. So the alternative to this part is to just say, instead of creating, the alternative to the entirety of this, including all of this, is to just create a heap that has all the elements in A. So I would just say H is make heap of A. Did I call it make heap before? Wait, what did I call it before? Yes, make heap. But I also gave it N, so let me make heap of A and N, right? So alternatively, I can do this. If I want to sort all the numbers in A, I can just make a heap out of A, and then I can just keep taking out the maximum element and printing it, right? Now, unfortunately, this doesn't really improve your time, because previously we saw that heap sort is taking O(n) log n, and now I'm improving this part. This part used to take O(n) log n too. Now it's only taking O(n). But the next part is still taking O(n) log n, right? So overall, I'm still spending O(n) log n to do heap sort. But I mean, in practice, this might be a little bit faster. Okay. Now, here's the really interesting part. You actually cannot do it any faster than this. So we will prove that for at least some families of sorting algorithms, it's impossible to come up with an algorithm that works in better than n log n time. And then literally the session after that, I'm going to show you a sorting algorithm with linear runtime. So, but for now, I just want to do one more thing. And it's talking about this sum that happens a lot. So I just want to put it here. So we had this sum of I times 2 to the power of I, right? Another way of looking at it is that if I call 2 to the power of I to be j, it's like j times log of j, right? So let's say I have a sum like this. I have the sum of j from 1 to n of j times log of j. And again, this is basically the same sum as this one. It's just that instead of I, I'm saying log of j, and instead of 2 to the power of I, I'm saying j. Okay. So what is this sum? If I just sum up all the numbers from 1 to n and take j times log j. Okay. Or actually, I can even do a more simplified version. What if I just take the sum of log j and log base 2 of j, let's say, for j from 1 to n. Okay. This is actually going to be in theta of n log n. Okay, so I want to prove this. I just want to prove that this is in theta of n log n. But before that, I want you to also realize that this is basically the log of n factorial, right? Because the log of a times b is just log of a plus log of b. So log of n factorial is just the sum of all the logs from 1 to n. So basically, what I'm proving here is that the log of n factorial is within a constant factor of n log n. It's in theta of n log n. Now, the proof is not that hard. So let's look at this sum, j from 1 to n log of j. Do you agree that this is less than or equal to the sum of j from 1 to n, just log of n? Because j is less than n, I'm just over approximating, putting n there. So this is n times log n, right? So this part shows that our sum or log of n factorial is basically in O of n log n, but I want to show the other side as well. I want to show that it's in omega of n log n. So here's the thing. Let's say I take the sum of j from 1 to n of log of j. This is the sum of a bunch of logs, and the logs are getting bigger and bigger as I'm going forward in the sum. So I just say, let's drop the first half. Okay, so this is definitely greater than or equal to the sum, the exact same sum, log of j, but now j starts from n over 2 and goes all the way to n. I'm just dropping the first half of the items in my sum. It can only make it smaller, right? But now, since my j is at least n over 2, log of j is at least log of n over 2. So this is greater than or equal to the sum of j from n over 2 to n, log of n over 2. But log of n over 2 is log of n minus 1. So this is greater than or equal to sum of log of n for j from n over 2 to n, and then at the end, minus n over 2, whatever. Okay? Or actually, I can just write it like this, log of n minus 1. Now, here's the thing. From n over 2 to n, I have n over 2 elements plus 1, right? And so basically, I have n over 2 times log n minus n over 2, right? So this is n over 2. Well, again, there is a plus 1 there. Let's write it like this. It's in theta of n over 2 log n minus n over 2. But again, this is just n log n, right? Or actually, I don't even need the theta. I just need the omega part. So since I'm using asymptotic notation, I don't care about these constants. And also n log n is greater than n in magnitude. So I don't care about the minus n. It's the n log n that stands. So this is in omega of n log n. And yeah, so my log of n factorial was in omega of n log n. So by definition, it's in theta of n log n.